Part 10 of mathematical physics. Let's continue the previous topic of complex number. This video start with liouville theorem. If a function fz is analytic for all finite value of z and is bounded and is a constant, then f dash a magnitude is less than equals to m by r. As r tends to infinity, f dash a mod is equals to 0. Here fz must be constant. Now some theorem of liouville theorem. Theorem 1. This is Gauss mean value. Let fz be analytic inside and on a circle C with center with center at A. Then Gauss mean value theorem state that f of A is the mean value of all the value of fz on C. Now theorem 2, this is called maximum modulus theorem. If fz is analytic inside and on a simple closed curve C, then the maximum value of mod of fz occurs on C unless fz is constant. Now theorem 3, this is called minimum modulus theorem. If fz is analytic inside and on a simple closed curve C, and if fz does not equals to 0 inside the curve C, then mod of fz has its minimum value on C. Let's do a question on complex integration. around our rectangle. Case is given, coordinates of rectangle is given 2 plus minus iota, comma minus 2 plus minus iota. Let's do this question. First of all, we need to plot these points. Here this is a rectangle. So this is 2 plus iota, and this is 2 minus iota, and this is minus 2 minus iota, and this is minus 2 and plus iota. These are the coordinates. Let's do integration. Here this is given condition. Here this is z square minus 1, so we can write this z minus 1 into z plus 1. Here using here Cauchy integral, first of all we need to evaluate this integral, and using here Cauchy integral, here these are the poles, so using here Cauchy integral theorem, now putting this value here, fz is cos pi z divided by z for this first we need to write this like that, plus integration of cos pi z divided by z plus 1 dz. Now using here Cauchy integral, at z equals to 1 plus 2 pi I f of z, z equals to minus 1. Here this is fz and this is also fz for this case. Now putting z is equals to minus 1 in this integral, in this fz, plus 2 pi I, and putting here in this z equals to 1, so this become this. Here this become minus pi I, as cos pi is minus 1 plus 2 pi I, and cos pi also minus 1, so this equals to 0, so this integral becomes 0. Cos pi z dz divided by z square minus 1 equals to 0. Let's do another question. Mode of z equals to 2, and here C is a circle, so As you can see here, z0 is equals to 0. For in complex number, circle equation is written as this. And here you can see radius is equals to 2. So center is at 0 origin and radius is at 2, so circle becomes this. And here you can see z equals to z whole power 3 is equals to 0. If we put here, so z is equals to 0 comma 0 0. So pole is 0 and order of pole is 3. If order of pole is more than 1, so we use here this identity. dz. So this is n plus 1. Now here you can see this is a z raised to power 3, so n equals to 2. So putting this value, so put n equals to 2. And we can write this. Now integral e raised to power iota z divided by z cube dz is equals to 2 pi iota divided by 2 factorial. This term is go here divide into here, this 2 is represent differentiation. So we differentiate the value of fz and putting the value z equals to 0. On differentiating this, we get 2 times iota, so this become iota square and z equals to 0. Putting z equals to 0, we get here minus pi iota. Now another topic is residue. After starting this topic residue, we know that what is singularity and their classification. Now singularities and infinite series. Singularity points, if A is a singularity or a singular point of a function, is the point where the function ceases to be analytic. For example, z is equals to 0 is a singularity for f of z equals to 1 by z. Here if we put here z equals to 0, fz becomes infinite. Now classification. Isolated singularity. For z equals to a is said to be an isolated singularity if fz is not analytic at z equals to a, and there exists a neighborhood of z equals to a containing no other singularity. For example, sin z divided by z minus 1 to z minus 2 has isolated singularity at z equals to 1 and z equals to 2. For fz is equals to cos 1 by z. For this fx having singularity at 1 by z equals to 2n plus 1 pi by 2. Here on solving this, z is equals to this value, or for different value of n, we get this value. And for this case z equals to 0 is a non isolated singularity. Now another removable singularity. If z equals to a is called removable singularity of fz if limits z tends to a fz exist finite value. For example, f of z is equals to sin z divided by z has removable singularity at z equals to 0. Now another poles. Here fz is equals to z plus 1 whole square into z minus pi by 2 whole cube. Here z at poles at z equals to minus 1 have order of 2 and poles at z equals to pi by 2 having order 3. Now another essential singularity. If there exists non-finite value of n such that limit z tends to a z minus a whole power n fz exist finitely, then z equals to a is set to an essential singularity. For example, f of z is equals to e raised to power 1 by z has essential singularity at z equals to 0. If we expand 1 by z, you can see here you can see there are infinite number of inverse terms. So this is also an identification for essential singularity. Let's do some question for finding singularity. F of z is equals to cot pi z divided by z minus a whole square. Here z equals to a is a pole of order 2 and expansion of cot pi z, we can write cot pi z is equals to cos pi z divided by sin pi z. So cot pi z have singularity at pi z equals to n pi. Comparing this term, n equals to 0 for sine value equals to 0 only at n pi values. So if we multiply z minus n into cot pi z equals to z minus n cos pi z divided by sine pi z, and taking limits z tends to n, this equals to limit z tends to n z minus n cos pi z divided by sine pi z. So z is equals to n poles. Here this become finite value, finite number. So the limits point of this pole at z equals to infinity is essential singularity. Now let's do another question. F of z is equals to tan 1 by z, or we can write tan 1 by z equals to sine 1 by z divided by cos 1 by z, and for putting this value equals to 0, so 1 by z equals to this value. So z equals to 0 is a limit point of these poles. Hence, it is isolated essential singularity. Now let's do another question. F of z is equals to sine 1 by 1 minus z. Here 1 by 1 minus z is equals to n pi. If we put here 1 minus z equals to 0, so then this equals to this. On solving this, z is equals to 1 minus 1 by n pi. Here z equals to 1 is a limit of these zeros. So this is also case of isolated essential singularity. Now let's do infinite series. A series in the form of this is said to be power series in z minus z naught. Here this z is complex variable and z naught is the center of the series, or we can expand this. Z minus z naught whole power 3 up to so on. Here at center z equals to z naught equals to 0, we can write this summation equals to a n z raised to power n, and on expanding this we get this term. Now region of convergence. The region of convergence is the set of all points Z for which series converge. There are three distinct possibilities for a convergent series. First is series converge only at Z equals to Z naught. The series converges for all points in the whole plane. Third is series converge everywhere inside a circular plane Z minus Z naught greater than or less than R, where R is radius of convergence and diverge everywhere outside the circle or circular ring. Now, for finding radius of convergence of power series, formula used is 1 by R equals to limits n tends to infinity mod of an raised to power 1 by n. Second, 1 by R is equals to limit n tends to infinity mod of an plus 1 divided by an. Let's do some question on this topic. This is fz is given, so we need to find the radius of convergence of fz. Here using this identity for finding radius of convergence, we can write r equals to limit n tends to infinity an divided by an plus 1. These are very simple question. In this question we put the value of n and n plus 1 in the given condition. Here r is equals to limit n tends to infinity. Here an is equals to 1 by n and an plus 1 is equals to 1 by n plus 1. Now put this value in this formula, we get this value. Now let's do another question. Here you can see this is given this value. This z is z minus z naught. So we similarly use this formula here and finding radius of convergence. Now putting an equals to 1 by n plus 1 whole power 3 4 raised to power n and an plus 1, putting here in place of n plus 1, we get this value. Now putting this value in this formula, here this is n tends to infinity Here this power is cancelled out by this power, and we can take common n cube in both terms. So we can write here 1 plus 2 divided by n whole cube divided by 1 plus 1 by n whole cube into 4. Here if we put here, now putting the value of n, this term becomes 0 and this also 0. So the answer is come 4. Here you can see that mod of z plus 2 is less than 4. Now let's do another question. Minus 1 raised to power n minus 1 into z raised to power 2n minus 1 divided by 2n minus 1 factorial. This is fx given. So first of all we need to find an. An is equals to minus 1 raised to power n minus 1 divided by 2n minus 1 factorial. Here we need to put here n equals to n plus 1. So we get here this value 2n, this equals to 2n plus 1 factorial. Now putting this value in radius of convergence formula, here first we need to put the value of an. Here an is equals to minus 1 raised to power n minus 1 divided by 2n minus 1 factorial, and we need second we put this value an plus 1. So this value comes here divided by minus 1 whole power n, and this power is cancelled out by this. And if we solve this factorial, we can write here 2n plus 1 into 2n minus 1 factorial minus here and 2n minus 1 factorial, and this is mod limit n tends to infinity. This cancel out by this. So if we put here infinity, this equals to infinity. So this converge absolutely for all z such that mod of z is less than infinity. Now Taylor's theorem. Let fz be analytic inside and on a simple closed curve C, and A plus H be 2 points inside C. So f of A plus H we can write here in this form. F double dash A plus H cube divided by factorial 3 F triple times differentiation plus up to so on plus H raised to power n factorial n F and A. Put z equals to A plus H and H equals to z minus A in this equation. We get the value of fz. This is a square and divide by factorial 2. z minus a whole power 3 divided by factorial 3 times differentiation of fa up to z raised to power n divided by factorial n time differentiation of fa. Here you can see it is converge for z minus a less than r. If we put a equals to 0, then f of z equals to this. F double dash 0 plus up to z raised to power n factorial n f raised to n times differentiation of f0, and this series is called Maclaurin series. Here some important expansion. We can write e raised to power e raised to power z equals to this. So this is z raised to power 4 divided by factorial 4 up to so on. And ln 1 plus z is equals to z minus z square divided by 2 plus z cube divided by 3 plus up to minus 1 raised to power n minus 1 z raised to power n divided by n. Here this is for mod of z is less than 1. This may be different for when z is greater than 1. Now for sin z, you can write in summation form minus 1 raised to power n minus 1 x raised to power 2n minus 1 divided by 2n minus 1 factorial. This is for n equals to 1 to infinity. And similarly for cos z, you can write minus 1 raised to power n minus 1 x raised to power 2n minus 2 divided by 2n minus 2 factorial. And expansion of 1 plus z raised to power p, you can write this. Divided by 2 factorial plus p into p minus 1 into p minus 2 divided by 3 factorial z cube up to so on. Let's do a question on Taylor series. Fz is given and we need to expand about z equals to 2. So first of all we find f2. Putting here the value of z equals to 2, we get here minus 5 by 2 and differentiate fz, and putting z equals to 2 we get 3 by 4. And similarly if we differentiate 2 times and putting z equals to 2 we get minus 13 by 4. Now putting this value on Taylor series expansion, here first we need to put fa. So fa is f2, so this, and second is this value 3 by 4 z minus 2. Here we expand about z equals to 2, that's why we use here z minus 2 here. Next is minus 13 by 4 into factorial 2 z minus 3. whole square up to so on. Let's do another question. F of z is equal to summation an z raised to power n. Here mod of z is less than r and mr is the upper bound of mod of fz on the circle mod of z equals to r. Here small r is less than capital R. We need to prove mod of an into r raised to power n is less than equals to mr. So this is a question of Cauchy inequality. Are using here Cauchy integral. Using here fz is equals to summation n equals to 0 to infinity an z raised to power n as it is given. If we find n time differentiation of fz and putting after z equals to 0, so we get this value. So we can see here an is equals to 1 by factorial n time derivatives of f0. Here now using here Cauchy integral, factorial n divided by 2 pi iota integral fz divided by, here this is a formula for this. Here we use here f0, so put here f n time derivative 0 equals to factorial n divided by 2 pi iota closed integration of fz divided by z raised to power n plus 1. Here z is equals to r into iota theta. As we know, this is a form of complex number. So using here, and if we differentiate, dz is equals to iota r e raised to power iota d theta. Now putting this value in this integration, r into iota e raised to power iota theta d theta divided by r raised to power n plus 1 e raised to power n plus 1 iota theta. Here we put the value of z in this value, we get this value. Now here we find the value of an is equals to 1 by factorial n f n times derivative 0. So first of all we used here Cauchy inequality. After doing this integration we get this value, and using here Cauchy inequality we can write here this, and if we find the value of this an is equals to this value 1 by n factorial into f n time derivative. So we put the value of this here, we get this value, and this 2 pi is cancelled out by this 2 pi, so we get this value. And we can multiply by both sides r raised to power n. we get this, hence proved. Now another important theorem, Laurent's theorem. If we require to expand fz about a point where fz is not analytic, then it expanded by Laurent series, not by Taylor series. Like that, fz is equals to a0 plus a1z minus a plus a2z minus a whole square up to b1 divided by z minus a plus b2 divided by z minus a whole square up to so on. Here we can write this in expansion form. Summation bn z minus a power minus n. Here an is equals to 1 by 2 pi iota integration of curve 1 fw divided by w minus a n plus 1 tw, and bn is equals to 1 by 2 pi iota integration of closed curve 2 f omega divided by omega minus a minus n plus 1 dw, so d omega. Let's do a question on Laurent's theorem. F of z is given as e raised to power 2z divided by z minus 1 whole power 3, and given that z equals to 1. Let here, for this type of condition in which this like term are present, we put u equals to z minus 1 or any t equals to z minus 1. So fz is equals to e raised to power 2u plus 1 divided by u cube, or we can write here like that. Now this is u. Now expanding e raised to power u, we can write here this is 2u. Up to so on, and multiply this u cube, we get this value plus 8 by 3 factorial plus u by 4 factorial up to so on equals to, now putting the value of u equals to z minus 1. Now this become this, so this is square plus 4 divided by factorial 2, this equals to 2, and divided by z minus 1 whole cube plus 8 by 6, sorry, we can write here 3 factorial plus here z minus 1 divided by 4 factorial up to so on. Now let's do another question. F of z is equals to 1 by 1 plus 1 by z plus 1 into z plus 3. Here given that 1 is greater less than of mod of z and mod of z is less than 3. Now for this type of condition, here you can see z is less than 3, so this type of question is solved. First of all, we need to make them separate, so multiply by 1 by 2 and divide, multiply by 2 and divide by 2, we can write this term as like that: 1 by z plus 1 minus 1 by z plus 3. So the condition is given: 1 is less than z and z is greater than 3. So taking bigger term common, so in this term z is greater than 1, so z is taken common, so we can write this. And in this term z is less than 3, so 3 is taking common. Now we can write this term like that, and also this term. Now expanding this term: 1 by z, 1 minus 1 by z plus 1 by z square minus 1 by z cube up to so on, minus 1 by 3. Now expanding this term: z by 3 plus z by 3 whole square minus z cube divided by 27. Here we can also write this: z square divided by 9 and up to so on this. Now multiply this 1 by z in this term and 1 by 2 and 1 by 3 also. So we can write this: up to so on minus 1 by 6 equals into 1 minus z divided by 3 plus z square divided by 9 up to so on. Here we can write this in general form: summation n equals to 0 to infinity 1 by 2 into minus 1 raised to power n z raised to power n plus minus n plus 1 minus 1 by 6 minus 1 raised to power n z by 3 whole power raised to power n. We will discuss calculus of residue in upcoming video.